Konstantin Zarembo from Uppsala in today's colloquium. Konstantin has been here in Sweden since 2001, and I now heard recently that unfortunately it seems Sweden will lose him since he got a very prestigious position at École Normale in Paris. Konstantin is very well-known theoretical physicist in his generation. He received his education in Moscow. He did a postdoc in Vancouver with Gordon Semenoff, and after that came here to Sweden, and he is very broad in his research, made contributions to string theory, condensed matter physics, statistical physics, and recently made a very important contribution to supersymmetric gauge theories, about which he will tell us today. So please, Konstantin.
Thank you, Edwin. I'm very pleased to be here and to give a colloquium. So the contents are clear from the title. So I'll try to explain how spin chain strings and gauge theories are related. Though a priori these are three very different subjects that, although has been studied quite a lot in theoretical mathematical physics. So gauge fields or Yang-Mills fields form the basis for our current understanding of fundamental interactions. So the simplest gauge field is the electromagnetic field. And quantum theory of electromagnetic fields is probably the most accurate theory we have. So the trademark of this theory is the calculation of anomalous magnetic moment of mu that is known both experimentally and theoretically with unprecedented accuracy of 10 digits. And I guess, well, experimental accuracy is going to improve, but the theory has reached its limits. And the reason it reached its limits is that the contribution of strong interactions to this number are about of the same order as the theoretical error here. So when gauge fields are weakly coupled, and this is the case for QED and electroweak theory, the theoretical control over calculations is very good. We can compute any quantity with, well, if necessary, with arbitrary accuracy by perturbation theory. And so now the accuracy is okay. As I said, it ranges from 10 digits to 3 digits for certain quantities, but for the theory of strong interactions, QCD, it's not the case. So we cannot compute with arbitrary accuracy, say, the hadron masses. So the reason for that is that the coupling constant of strong interactions, in fact, is a function of energy, and it grows at low energies. So even though it is small at energies of, say, 10 GeV or even 1 GeV, and there one can use the perturbation theory to make predictions. At low energies, the QCD loses its predictive power, and because the coupling constant gets rather big. In fact, so this expression, it's the famous formula of asymptotic freedom. It is obtained assuming that the coupling is sufficiently small, and if we literally use it for arbitrary energy, then at some energy the effective coupling becomes infinite, and so this is the dynamically generated scale of QCD, which is, roughly speaking, 200 MeV. So really, of course, the coupling doesn't blow up at this scale. It's just the theory becomes strongly coupled, and we don't know how to do calculations there. So it loses predictive control at low energy scales, and so the situation is sort of very unpleasant for a theoretician because all the equations are there. We know how to write down the basic equations for strong interactions. These are quantum Yang-Mills equations, but we don't know how to solve them. Now, the fact that the coupling grows in the infrared leads to certain very complicated and interesting dynamical phenomena like color confinement. So if we compare QCD and QED where we insert two external sources, then the behavior is very different. So in QED, the sources, the Faraday lines of electric fields spread in space and lead to the potential that grows at large distances but very slowly, so just the Coulomb law. But in QCD, it is believed that because of the dynamical effects, the Faraday lines pinch into a tube of finite thickness. So this tube obviously has constant energy per unit length. So if the external sources, color sources, are sufficiently far from one another, the potential is just equal to this energy per unit length times the distance. So the potential is linear and it confines quarks inside hadrons. So this is a qualitative picture of quark confinement. But actually it is very well confirmed by whatever we know about strong interactions, in particular by numerical simulations of QCD. So the interquark potential is now computed to very high accuracy, and you see that it's at large distances it is to high accuracy linear. Now more refined calculations shows that this flux tube that connects Faraday lines of chromoelectric flux actually fluctuates. So it behaves in some sense as a string with finite tension. So this has led many people to think that maybe Yang-Mills fields can be somehow reformulated in terms of theory of strings, so that strings are basic dynamical constituents of strongly interacting Yang-Mills fields, at least at large distances. Now in this flux tube picture, it seems that string theory may only give qualitative description at distances that are larger than the thickness of the tube. But surprisingly, this point of view has been challenged in recent years, and it is now clear that at least in many cases, Yang-Mills fields can be exactly described by the idealized infinitely thin strings. So this sort of rings of glue. So if we don't have any sources, then we can imagine these fluxes of chromoelectric Faraday lines to form closed tubes. And the common law that these closed strings of glue are described glue balls, so particles made entirely of gluons. And the open strings that stretch between quarks and antiquarks correspond to mesons. Now this is just a common law, and again this new developments show that it's not quite correct, so it's not correct in details. Now, what is a theoretical way to connect strings and gauge theories? Well, one idea that was sort of pursued in this direction is the large N expansion. So the idea is the following. In strong interactions, the quarks and gluons come in 3 colors, but it is convenient to keep the number of colors as a parameter. We can consider a theory where the number of colors is equal to n, and in fact we can regard 1 over n squared as a small parameter. So in reality it's 1 over 9, so indeed 1 over n expansion estimates show that it works with an accuracy of about 10%. So if you could understand even the ultimate limit where n is infinite, then probably could say something about really strong interactions. Unfortunately, this, although there are some simplifications that occur in the theory at infinite n, they are not enough to solve it. But it is possible at the qualitative level to establish relationships to strings. So, first of all, how the parameters scale in this limit. From this asymptotic freedom formula, we see that the coupling constant should actually scale with n, because the okay, this formula shows that 1 over g squared is shifted by something that's proportional to n. So instead of the coupling, it's convenient to introduce the combination lambda, which is the product of g squared and n, which is called the 't Hooft coupling. And it is this coupling that controls the strengths of strong interactions, in fact. And the other parameter is 1 over n squared. So that we will consider to be small, but the 't Hooft coupling, okay, it need not be small, so it can be large as well. So, but when it is small, we can do usual perturbation theory, and then we can organize it in a very nice way. So this was done by 't Hooft quite a long time ago. So since gluons have the same quantum numbers as quark and antiquark, we can draw them as, in the diagram technique, we can draw them as two lines. So then, so this each line for each color index, and then the diagrams are built from usual vertices, but the vertices are such that the number of incoming and outgoing lines are conserved. And this gives the diagrams of perturbation theory a two-dimensional topology. So they look like two-dimensional surfaces, and in fact the counting of this number of colors, or this color factor, is related to the topology of the diagram. So the diagrams that have the simplest topology, just which can be drawn on the plane, they are enhanced in the large n limit. So if we consider the simplest example of diagram with three gluons, then it corresponds to two large n diagrams. One is planar, the other is not, and the one that is not planar can be shown to be down two orders in n. So in the large n limit, if we take n number of colors to infinity, only planar diagrams survive. And if we imagine that at strong coupling, the diagrams with a large number of vertices dominate, then they sort of pictorially look like string world sheets. So this vertices, so this diagram is built of vertices and propagators, but each of these vertices is then integrated over space-time. So this is embedded, this is a two-dimensional surface embedded in space-time, but discretized. So maybe there can be some way to describe it as at least approximately, as a continuous two-dimensional surface, and that can be regarded as a world sheet of the string. So this string is a one-dimensional object. When it moves in space-time, it spans a two-dimensional surface which is its world sheet. So this is the qualitative argument that is usually given when people talk about strings and gauge theories. Now, the next logical step is to say that, okay, we don't understand, we cannot sum these diagrams, but at least we can write down some phenomenological model that has strings as sort of basic degrees of freedom, and try to fit it to what we know about strong interactions. Well, unfortunately, this doesn't quite work because of certain conceptual problems. So, first of all, it turns out that string theory describes gravity, so that whatever we do, there is a graviton in the spectrum of closed strings. This is a universal fact. Now, on one hand, it's good because then string theory is presumably the theory of quantum gravity, or at least it's a theory of quantum gravity. So we can ask within string theory many questions about quantum gravity. But in this context, we just want to describe Young-Mills fields using strongly interacting Young-Mills fields using strings. And then we don't know what the graviton is. So in the usual interpretation, so any closed string state should be associated with glue ball, the bound state of gluons, but there is no place for a massless spin 2 glue ball in Young-Mills theory. No Young-Mills theory has it. So there is something wrong with interpretation here. Now the second problem is a little bit more technical, but still serious, and namely that string theory is only consistent in 10 dimensions. So we only know how to formulate string theory in 10 space-time dimensions. And it's not clear how to deal with strings in when we are in the normal 3+1 dimension space-time. And finally, if you take the idea that gauge fields are equivalent to strings seriously, namely that there is some exact description in terms of strings, not just an effective large distance description, then strings should somehow remember that they are built of these discrete gluons, so they come from planar diagrams or something like that. So now the first two questions actually have an answer now. So the developments of recent years has shown how to overcome these problems. And the third question is also sort of answered, but not quite completely. So, so it is believed that large N expansion of Young-Mills theory is equivalent to string theory. And there are some toy models that were offered very early on when large limit was proposed, but it took 20 years to realize this in a 3+1 dimensional field theory, and the first model that really relates strings and gauge fields was proposed by Maldacin in 1997 and goes under the name of the idea CFT correspondence. And so it is the basis of our current understanding of how strings arise in gauge theories. So the proposal was that actually it was a conjecture. It was not proven, it is not proven yet, but it is undoubtedly true that Young-Mills theory, which is supersymmetric and which actually has largest possible number of supersymmetries in 4 dimensions, is exactly equivalent to string theory on the background that is a product of anti-de Sitter space and the sphere. So this is a 10-dimensional space, so there is no problem with 10 dimensions. As I will explain, it also solves the other 2 problems. So for instance, it allows to understand why gravitons is actually a welcome feature of string descriptions of gauge fields. So and this is just an interpretational issue. So we shouldn't interpret string states literally as particles in gauge theory. So they are not bound states like glue balls or mesons, but rather they are dual to local operators. So each string state is dual to some local operator in Young-Mills theory, and this solves a lot of puzzles because now graviton is not a massless glue ball, but it is just dual to energy momentum tensor. Energy momentum tensor naturally couples to gravity. And the masslessness of the graviton is just a reflection of conservation of energy momentum tensors. Now, extra dimensions is also not a problem, they just are geometric images of the energy scale and global symmetries of the theory. And finally, in this approach, the sum rules are often mathematical. So, the basic ingredient of this of the ADS-CFT correspondence is the holography, which is which is a term that which is used to describe or to denote the relationship of a theory in higher dimensional space to a theory in lower dimensional space. So, and it comes from the properties of anti-de Sitter space. So anti-de Sitter space has, in addition to 4 coordinates, 4 space-time coordinates, it has a coordinate z that ranges from 0 to infinity, and it has this metric. But anyway, so the most important thing is that gauge fields are supposed to live on the boundary of the space. So since z ranges from 0 to infinity, it has a boundary. But strings are allowed to propagate in the bulk. So they sort of fill more dimensions as gauge fields. In some sense, they're projected onto the boundary. And this projection is how the gauge fields and strings are related. So in particular, the strings in the bulk are infinitely thin, but in the course of the projection, they acquire some finite thickness. So, so this conjectured correspondence can be used to calculate correlation functions in gauge theory by considering propagation of strings in the bulk. So, if we consider a correlation function of 2 local operators, they are dual to some particular string state. So, if we insert them on the boundary, to compute this in string theory, we need to just insert this propagator of the string state between the points where operators are inserted. So this gives, this provides a qualitative explanation for what this extra coordinate z is. Because if you consider points that are nearby, the string cannot get too far from the boundary, so it stays at very small z's. But if the points are far away, then the string, of course, will shoot rather far, and so it will probe the larger distances in the z direction. So z is, in a sense, dual to the energy scale in Youngman's theory, because by uncertainty principle, short distances is equivalent to small momentum, small energies, or large momentum, large energies, and this means that near the boundary, the region near the boundary is responsible for ultraviolet behavior of gauge fields, whereas the larger values of that corresponds to smaller energies or larger distances in 4 dimensions. So in particular, in generalizations of this basic gauge string of the ADS-CFT correspondence, which have dynamically generated scale, work in a very simple way. So we just put some sort of infrared ball in the bulk, and this serves as an infrared scale for gauge fields. So near the boundary, the behavior of the metric is the same. Actually, I forgot to tell, but anti-de Sitter space has a very important property of scale invariance. So if you scale x's and z by the same factor, the metric stays invariant. So this means that the gauge theory describes as no scale. But then if you put this infrared ball in the bulk, then it generates some scale, because large strings cannot move beyond this wall. But still at short distances we have approximate scale invariance. And this is exactly what we expect from strong interactions. However, studying in detail the idiosyncratic correspondence is also very hard. And the reason for that is that the parameters, it is known how to identify the parameters, but both sides of this correspondence are complicated interacting theories, and they become simple and weakly coupled in different regions of parameters. So the string tension, so let's first look at the string coupling. So the string coupling is the ratio of 't Hooft coupling to the number of colors. So if you keep 't Hooft coupling finite or large and send the number of colors to infinity, then the string coupling goes to 0. So as expected, large and limit corresponds to free strings. But still the strings are allowed to fluctuate, so they have quantum fluctuations, and it's at the moment not completely clear how to take into account these quantum fluctuations, which are controlled by the string tension. So if the string tension is large, the string behaves basically as a stick. It's very hard to bend it. But if the tension gets small, the string becomes softer and it fluctuates a lot. So we understand very well the regime where the tension is big, but by this correspondence it corresponds to the large values of the coupling on the gauge side. So weakly coupled string describe strongly coupled gauge fields and vice versa. And in between we have some interpolation. So at weak coupling we know how to, so quantum effects in Yang-Mills theory are not so important. At strong coupling, the Yang-Mills fields are strongly fluctuating and they're strongly coupled. We don't know how to describe them in general. But then the strings become rigid and simple, and vice versa in the other direction. So there are examples of quantities that can be traced from weak to strong coupling. One particular example is a circular Wilson loop. So at weak coupling it is described by perturbation theory, and at strong coupling it basically is equivalent to the minimal area of an empty de Sitter space. Now these two descriptions actually have an overlapping regime of validity, but it doesn't help us to understand how they match in detail. So the matching between these two regimes, the understanding of it came from a rather unexpected direction. And to make progress in it, it was necessary to actually introduce a new concept in the relationship between gauge field and strings, namely it seems that there is an intermediate step related to spin chains. Now spin chains actually are very natural from the point of view of planar diagrams, because planar diagrams, and so this, how spin chains arise can be explained in terms of pictures. And the reason for that is that, again, there's this two-dimensional structure of a planar diagram, so that if we cut it at some time slice, then it will look like a collection of gluons, but these gluons are ordered in the color space because we know that this gluon stands to the left from that gluon and that stands to the left from that. So they are ordered because of their color charges. So if we cut this diagram at some earlier time slice, then we would find, well, sort of the same gluons but in a different quantum state, and they evolve in time in some way that is prescribed by, well, the way we should have calculated the diagram, although we cannot do it in arbitrary case. So anyway, the slice of a diagram can be characterized just by okay, we can look at each gluon and characterize by its quantum state. So, and the states are ordered because of this color ordering. So they do not include color degrees of freedom anymore. So this is just spin, momentum, etc. of the gluon. So the state can be naturally associated with a one-dimensional spin chain, because what is spin chain? We have points ordered along one-dimensional lattice, and at each point we have, say, spin or, okay, some quantum state. So the evolution operator for gluons therefore acts in this spin chain Hilbert space, and so it is associated with some sort of spin chain Hamiltonian. And so spin chains arise in many problems where one wants to sum particular series of planar diagrams. So one case in which it occurred is the so-called Regge limit QCD. It is the limit where we consider scattering of two hadrons in the regime where the center of mass energy, so usually denoted by S, so it's center of mass energy squared, in fact, is much larger than the transmitted momentum, usually denoted by minus T. So since there is a large scale here, it seems that we can use perturbation theory because the effective coupling is small, but this is not the case because of certain large logarithms that occur, and one in principle should resum this large terms in perturbation theory that contain the log in addition to the coupling constant. So this was done many years ago by Baletsky, Kuraev, Lipatov, and Fadin. What they found is that in this limit, the amplitude, the scattering amplitude, is dominated by exchange of sort of particles that can be considered as dressed gluons. So they have quantum numbers of a gluon, but they are not really gluons, so one has to resum many diagrams to get this description. And these particles also interact, so the amplitude is a sum of exchanges of bound states of these gluons, of these regions. And so the simplest of them is the two-particle bound state. It's usually called the Hart-Pomeroy. Then the bound state of three particles is called Oberon, and so on. And then one can derive the effective Hamiltonian that describes the bound state of n regions by essentially summing up a large series of diagrams. And in the large n limit, this Hamiltonian has the spin chain structure. So it is a Hamiltonian of certain spin chain of Heisenberg type. And the remarkable fact about the spin chain is that it's integral. So, okay, this allows to calculate how this amplitude behaves as a function of S. So now another instance where local operators, well, spin chains arise is the ADS-CFT correspondence, where the fundamental role is played by local operators. They're dual to string states. So one can ask, what is the Hamiltonian that describes local operators? And this operator is also a Hamiltonian of a spin chain. So just as a simple example, one can consider operators built of two constituent fields, and they're in one-to-one correspondence with the quantum states in the Hilbert space of a spin chain. So each field we associate with either spin up or spin down, and then they are cyclically ordered because of color indices. The natural analog of Hamiltonian here is the dilatation operator that describes the scaling dimensions of operators so that the correlation functions decay with some power law, and this power is an eigenvalue of this dilatation operator. Now that one can compute in perturbation theory, and it turns out to be precisely the Heisenberg Hamiltonian, which is a Hamiltonian of a one-dimensional ferromagnet. So at each site we have two-dimensional, 2 degrees of, not 2 degrees of freedom, but 2-dimensional Hilbert space, so spin up or spin down. And then there are spin operators, and the Hamiltonian is this one. Now this model, the Heisenberg model, is very famous, very famous model in mathematical physics. It's one of the first examples, or maybe the first example of an integrable quantum system that can be solved exactly. So it's an interacting theory. So there is no small parameter. Just that this overall scale doesn't matter because it can be absorbed into rescaling the energies. And then there are no parameters at all in the Lagrangian, yet one can completely find its spectrum. So let me describe how it is done. So since this is a ferromagnet, the ground state corresponds to all spins pointing in the same direction. And then one can build the spectrum by flipping these spins one after another. And so they propagate around the lattice with certain momenta. And these corresponding excitations are just magnets with various one-dimensional momenta. Now, interestingly, these have direct counterparts in string theory, so they are dual to so-called B-man states of the string. One can also consider more complicated states that are classical spin waves. So one can put, so these magnets behave as interacting bosons, so one can put arbitrary number of them in any particular momentum state. So this would correspond to some macroscopic spin waves propagating through the lattice. And those are not surprisingly dual to classical strings. And then there is a huge spectrum full of states that ends at the antiferromagnetic vacuum. So what these states correspond in string theory is a question that hasn't yet been answered. Now, the spectrum of all the states can be calculated, as I said, and the only two ingredients that are necessary to find the spectrum is the one particle energy and two body scattering matrix. So if you consider two spins that are well separated, we can scatter them on one another, and as a result of scattering, they will their wave functions will gain some phase shifts, which is described by this, which can be calculated easily and is given by this formula. So, and that's enough to build an arbitrary multi-particle state. So the idea is that if you have a many-body state, we just concentrate on one of these magnons, and for it, the other magnons are just scattering centers. So when its wave function goes from around the lattice, it gains phase shifts on magnon number 1, magnon number 2, magnon number 3, etc. So we can compute the total phase shift as the sum, linear sum of individual phase shifts on other particles. And the periodicity of the wave function then gives us the following equation for momentum. And so there are as many equations as there are particles in the state. So we just need to solve these equations for momenta, and then we find the energy as sum of single particle energies. So it's just illustrated here. So we have, if we pull one spin around the lattice and neglect interactions, then the total phase shift is just momentum times the length of the spin chain, because the wave function of particle with momentum oscillates with the phase proportion to the length of momentum. And so periodicity condition is just the quantization of momenta, integer units of 2 pi over the length. If you do a more refined analysis, then we should take into account pairwise scatterings. So, in addition to this momentum wave function, there is also a number of phase shifts, and then quantization of momenta is reduces to this beta equations. So for the Heisenberg model, they can be written in the algebraic form, and then the problem of diagonalizing this complicated quantum Hamiltonian reduces to solving a number of algebraic equations. Which can be solved numerically rather effectively or rather efficiently, or in thermodynamic limit they can be analyzed analytically. This was first done by Hulten in 1938. Now, from the point of view of supersymmetric Yang-Mills theory, this gives us a one-loop spectrum of all possible anomalous dimensions. But surprisingly, it's possible to generalize it to a non-perturbative level. So these beta equations just get more complicated. So part of the evidence for this comes from analyzing string theory that is dual to this Yang-Mills theory with n equal 4 supersymmetry, which so is living on the background ADS 5 versus 5. So it is described by some two-dimensional model that describes fluctuations of the string wall sheet in this background. I don't want to go into technical details, but effectively the problem reduces to some massive two-dimensional field theory that also turns out to be integrable. And integrability usually means that the system is solvable by beta ansatz. And the beta ansatz that describes this non-perturbative spectrum that is common to Yang-Mills theory and string theory is now known. It was proposed by Beisert and Staudacher 3 years ago. Unfortunately, the equations don't look very simple, but they are as they are. And also, there are some limitations to these equations, so they describe perturbation theory up to a certain order. But nevertheless, they interpolate between weak and strong coupling. And in some sense, this is a proof of this conjectured Malus-N duality, because we start with Yang-Mills theory, and then we continuously interpolate, and we end up with something that's equivalent to, that describes the string spectrum. So, let me come to conclusions. So the main conclusion is that there certainly is some relationship between gauge fields and strings, and the ADS-CFT correspondence is a witness to that. Now, it is not clear to what extent this relationship is universal, and which features are universal, which are not. One feature that is probably important and that should arise in other instances of gauge string duality is that an intermediate step in this relationship is a spin chain. So the gauge fields should be in some way are related to spin chains, which describe the constituent picture of planar diagrams. And then the continuum limit, or some sort of classical limit of spin chains should correspond to strings. So this picture sort of is so this relationship is mostly inspired by holographic duality, so this idea is CFT correspondence, and this is definitely one important ingredient in relationship between gauge and fields, that the gauge fields and strings, that strings live in space-time of higher dimension that is projected into the boundary where we have gauge fields. Now, the relationship to spin chains, and in particularly the property of integrability, has almost led to the exact solution of a four-dimensional field theory, which is supersymmetric Young's theory with an or supersymmetry. And apparently this is the first example, first case of a solvable Young's theory that we have in four dimensions. So although this solution is not complete yet, but it is clear that the complete solution can be found along these lines of studying beta equations and exploiting the property of integrability, spin chains, and their relationship to strings. Thank you very much.
So, thank you very much. Other questions, comments?
I mean, you start out from fundamental QCD, which is of course non-supersymmetric. So what can I extract from that for non-supersymmetric gauge series?
Well, people are working on that. It's you see, the spin chains first arose in this non-supersymmetric context, so in the description of the Regge behavior, and perhaps this description of the spin chains can be used in more instances. What is certainly clear is that many features of perturbative QCD at high energies are very much related to approximate conformal symmetry or scaling invariance of strong interactions. So the dynamical generation of scale is not important there. And then they become very similar to the supersymmetric Young's theory.
Alright, so if not, let's thank the speaker again.